we start now considering the case where the optic axis makes an angle alpha with respect to, this is the optic axis, with respect to epsilon 3, which is normal to the surface of the crystal. We still consider the case when we have a normal incidence. This is my epsilon 1 and this angle is alpha. The simpler case is to consider the d vector along epsilon 2. If d is along epsilon 2, after it enters, d will continue to be along epsilon 2. Why? There is no component of d along epsilon 3. And d component, normal component of d is continuous. So after it enters, there is no component of d along epsilon 3. So the only possible component of d can be along epsilon 2. We have already discussed whether it is possible to have component of epsilon 1. Again, by using the boundary conditions, one can show that that is not possible. So once the d is along epsilon 2, inside the crystal, that is the direction in which the ordinary ray travels, that is with that value of d. It will continue to be along epsilon 3. So let me draw that. That will correspond to a situation like this. D vector like that, and the velocity v p prime, I will write it as v is c by no epsilon 3. That will be there. Now let us consider the interesting case when d is along epsilon 1. Incident epsilon. The same argument that I used for d along epsilon 2 now is valid, and I have d transmitted is equal to d transmitted epsilon 1. But once it is inside, this is not in the direction of the principal axis of the index ellipsoid, and this angle is also alpha. Principal axes are eta 3, eta 1 and eta 2. Eta 2 of course coincides with epsilon 2. So given this, I can rewrite this as equal to d transmitted times eta 3 sine alpha plus eta 1 cos alpha. So I can write my E vector now. E would be d eta 3 by epsilon 3 sine alpha plus eta 1 by epsilon 1 cos alpha. Notice d transmitted and E transmitted lie in the eta 1 eta 3 plane, which is the same as the epsilon 1 epsilon 3 plane. So d transmitted, E transmitted and k are in the same plane, so that satisfies all the requirements. D transmitted is orthogonal to the direction of motion, that is direction of the wave, that is epsilon 3. My k here, I will write k incident is equal to k epsilon 3. We said that everything will be normal. So that condition is satisfied. B automatically satisfies that condition, and E is also in the same plane as D and epsilon 3. So now let's try to draw D. Let me draw it here. My D is along epsilon 1. If I want to draw E, this is my eta 1, eta 3, and this is my eta 1. Notice that epsilon 3 I have assumed to be greater than epsilon 1, so the component along epsilon 3 is contracted more than what it is done here. So that component, this should be perpendicular to epsilon 3 like that. So the vector d, E will be in that direction. and let's call this angle alpha. We have seen the ray which is found from the pointing vector, which is E cross B by mu naught, will be perpendicular to E, so that will be the direction of the ray. And with epsilon 3, this angle is beta. Sorry, because I've called that angle alpha, I call this beta. So this is beta. I can evaluate beta because I know D, this is a unit vector. I have to convert this into a unit vector. It will be E times a unit vector E transpose cap, which I will write it here. E transpose cap is nothing but eta 3 sine theta sine alpha by epsilon 3 plus eta 1 by epsilon 1 cos alpha, and I have to normalize it, so I write sine squared alpha by epsilon 3 squared plus cos squared alpha by epsilon 1 squared to the power half. Now, if I want to calculate beta, I just have to take the dot product of E unit cap and D unit cap, and let's just do that, and I will write that here. So, E cap dot D cap is nothing but sine squared alpha. E cap dot D cap is sine squared alpha is sine squared alpha by epsilon 3 plus cos squared alpha by epsilon 1 divided by square root of sine squared alpha by epsilon 3 squared plus cos squared alpha by epsilon 1 squared to the power half. So this gives us alpha, and this is cos beta. So let me redraw the picture once more. Before I do that, let me just say, notice epsilon 3 is greater than 1 and epsilon 1 is also greater than 1. So what is happening here? So this factor is less than 1. If I pull out, say, this factor is less than 1, and this factor is also less than 1, but I have a square root, so that makes it smaller. So this entire larger, so this thing, one can show that this number is always less than 1. That's quite straightforward. I will not do that here. Okay, now let me redraw the picture. Here is my incident ray, here is my D, that's my eta 3, and this is one ray. The other one, because eta 1 is in that direction, my D, this is my D transmitted, E transmitted will be in that direction. So my K ray will be and this angle will be beta, and that angle was alpha. So we will see when we try to draw wavefronts in the next video how to understand all this in a very physical way. We will be able to derive the same equation in a looking at the envelope using the Huygens principle. That will be part of the next video.